the country that pioneered high-speed rail with its famous bullet trains. Japan is now developing the next generation of bullet trains using a technology called maglev, which stands for magnetic levitation. Nestled in a Japanese mountain pass is one of the world's most extraordinary technological marvels, a 43-kilometer-long magnetic levitation train track. This track will also play a significant pivotal role in the inaugural intercity maglev train, seamlessly connecting the bustling metropolises of Tokyo and Osaka. Maglev trains stand out by using magnetic repulsion to lift and propel the train cars, enabling them to reach speeds exceeding 600 kilometers per hour, almost double the speed of traditional bullet trains. But how exactly does maglev work? And what are the challenges and benefits of this cutting-edge technology? Despite the many benefits that maglev trains offer over traditional high-speed trains, the only operational high-speed maglev line spans a mere 30 kilometers, linking Shanghai Airport to the city. The train completes this swift journey in just 8 minutes. However, the short track somewhat diminishes the advantages of high-speed maglev. By the time the train reaches its optimal speed, it's compelled to slow down. A 30-kilometer journey in 8 minutes translates to an average speed of 225 kilometers per hour, slower than the top speed of traditional high-speed rail. The proposed future network of high-speed maglev tracks spans only 400 kilometers, which is short compared to the extensive 60,000-kilometer network of regular high-speed train tracks already crisscrossing the globe. With an additional 50,000 kilometers under construction, why is this gap so large? Let's delve deeper into how maglev trains work and explore the reasons behind their restricted development. The maglev system, which leverages magnetic forces to levitate and propel objects, is very different compared to conventional trains, which rely on rails and wheels. Maglev trains float above a guideway, which is a track that has magnets embedded in it. The train cars also have magnets called electromagnets, which are coils of wire that produce a magnetic field when an electric current flows through them. Controlling the polarity and intensity of these electromagnets allows for the lifting, acceleration, deceleration, and stabilization of the train. How does this system work? The maglev system used by the Japanese trains is known as electrodynamic suspension, EDS, relying on superconducting electromagnets. Superconductors, materials with zero electrical resistance at extremely low temperatures, can carry a substantial current without energy loss. This feature enables the generation of a powerful magnetic field crucial for levitating the substantial train cars. The train is set in motion by wheels until it reaches a speed of approximately 100 kilometers per hour, 62 miles per hour, the minimum speed required for levitation. Then the electromagnets become activated, which causes the train to hover about 10 centimeters above the guideway, eliminating the friction and noise associated with wheel contact. Switching the polarity of the electromagnets initiates a push-pull mechanism, influencing the acceleration and deceleration of the train. The front electromagnets, sharing the same polarity as the guideway, propel the train forward through repulsion. Meanwhile, the rear electromagnets with an opposite polarity attract the train backward. Precise control of the train is achieved by altering the current and position of the electromagnets. Stabilization is maintained by feedback control systems that dynamically adjust the current and position of the electromagnets based on the train's speed, distance, and tilt. This intricate control mechanism ensures that the train adheres to the optimal path, avoiding swaying or wobbling. Aside from its speed, this EDS system presents numerous advantages over traditional trains, one of which is noise control. Compared to conventional trains, the maglev generates minimal noise free from engine or wheel-related disturbances, common sources of noise pollution. The only audible sound emanates from air resistance, which is minimal at lower altitudes and further mitigated through aerodynamic design and tunnel ventilation. It also mitigates vibrations. By eliminating mechanical contact with the guideway, the maglev train avoids the vibrations and wear and tear associated with traditional rails and wheels. This not only enhances passenger comfort and safety, but also reduces both train and track maintenance costs. It is considerably safer compared to traditional trains. The maglev train features a high level of automation and redundancy, minimizing risks related to human error and mechanical failures. Emergency wheels are equipped for deployment during power outages or malfunctions, allowing the train to safely drift to a stop. Additionally, the design incorporates features to withstand earthquakes and other natural disasters prevalent in Japan. The maglev train faces significant challenges, particularly in temperature and power consumption. Achieving superconductivity in the electromagnets necessitates cooling to an extreme temperature of -269 degrees Celsius, demanding substantial energy and intricate cooling systems. This temperature differential introduces thermal stress and condensation, potentially impacting the system's performance and durability. In terms of power, the maglev train consumes a considerable amount, especially during acceleration and levitation. The electricity is supplied by power lines along the guideway, which can be vulnerable to fluctuations and interruptions, increasing operational costs and the environmental impact unless sourced from renewable energy. The maglev train is also notably expensive to build and operate compared to conventional trains. The guideway alone costs about 10 times more than a traditional rail track due to the need for magnets, power lines, and tunnels. The train cars also incur higher costs due to electromagnets, cooling systems, and emergency wheels. The estimated total cost of the Tokyo-Osaka maglev train is about 9 trillion yen, approximately $82 billion, making it one of the most expensive infrastructure projects in history. The Japanese maglev train project has implemented innovative solutions to tackle these problems. Cryogenic cooling utilizes liquid helium, the coldest substance known, circulated through pipes inside the electromagnets to maintain a constant temperature. The liquid helium is recycled, reducing waste and cooling system costs. Additionally, the system employs regenerative braking, converting kinetic energy into electrical energy for storage or reuse, decreasing power consumption, heat generation, and brake wear. The maglev train features emergency wheels for power outages or malfunctions, allowing the train to safely drift to a stop. These rubber and steel wheels can also propel the train at lower speeds until it reaches the minimum speed required for levitation. Operating primarily in tunnels minimizes air resistance and system noise, offering protection from adverse weather and terrain conditions and ensuring system stability and safety. Tunnels are equipped with ventilation fans to regulate air pressure, temperature, noise, and exhaust. In 2017, the maglev train achieved a significant milestone with a successful long-distance test covering 286 kilometers from Tokyo to Nagoya in just 40 minutes. With passengers on board, this test not only demonstrated the speed and comfort of the maglev train, but also validated the reliability and safety of the system, emphasizing the feasibility of the project. The following year, in 2018, the maglev train opened its doors to the public, offering rides to selected visitors on the Yamanashi test track, a 42.8-kilometer segment of the guideway. Visitors experienced impressive speeds, reducing the travel time between Tokyo and Osaka from 145 minutes to just 67 minutes. The maglev train has not encountered any serious mishaps during its test runs, except for a tunnel collapse that killed a construction worker in 2021. The tunnel collapse occurred during the construction of the maglev train project in Nakatsugawa, Gifu Prefecture. This unfortunate incident resulted in the death of a 44-year-old construction worker, and another man was seriously injured. This was the first fatal accident connected to the enormous magnetic levitation train project. Despite this incident, the Japanese maglev train has maintained a strong safety record in its day-to-day operations. Looking forward, the third phase of the project aims to share and export maglev technology to other countries, particularly in Asia, Europe, and North America, already garnering interest and investment from nations such as China, India, South Korea, Taiwan, Germany, France, the UK, the US, and Canada. Maglev technology holds the potential to revolutionize the global transportation system. This innovation promises faster, safer, and greener connections between major cities and regions. Japan's commitment to this futuristic technology traces back to its history of pioneering train advancements, starting with the introduction of the world's first high-speed train, the Tokyo to Osaka Shinkansen line in 1964. The journey began in the 1970s with the construction of a 7-kilometer testing track in Miyazaki, where prototypes reached speeds of 60 kilometers per hour in 1972. By 1995, trains that could speed up to 411 kilometers per hour had been deployed. As the Miyazaki test track proved inadequate, the Yamanashi test track, conveniently situated between Tokyo and Nagoya, began construction in 1990. Here, the design transitioned from a prototype to a fully functional train capable of carrying 700 passengers in 12 cars at 500 kilometers per hour speeds. High-speed maglev trains go beyond scientific experimentation, presenting an efficient and rapid mode of transportation. However, their development poses not just an engineering challenge, but an economic one, as they compete against cars, planes, and other train types. In the US, the notion of traveling between New York and LA in 7 hours is often presented as a testament to maglev's potential. Despite the economic challenges, the efficiency and time-saving attributes of high-speed trains make them a compelling option, enhancing overall economic productivity. The Japanese maglev train project not only claims the title of the world's fastest and most comfortable train, but also sets a benchmark for futurism and eco-friendliness. Envisioned to bring economic growth, social cohesion, and environmental preservation benefits to Japan and the world, the maglev train embodies Japan's visionary spirit and determination to overcome 21st century challenges. It symbolizes a commitment to a sustainable and advanced future in high-speed rail, serving not just as a mode of transportation, but as a representation of Japan's leadership in innovation and engineering. What are your thoughts on the maglev train? Would you consider riding it in the future? If you like this video, click on the screen to watch other videos like this one. Don't forget to like, subscribe, and click on the notification bell to get notified when we post a new video.